of your school by Professor Emanuel Henn from Institute of Physics in São Carlos. So he's going to talk about Bose-Einstein Condensates and applications in quantum technologies. And I have a short announcement. Who wants to do questions, please, of course, feel free, anytime, right? But we need to do using the microphone. So when you want to do questions, please ask me or Anna, and we will give you the microphone for the questions, okay? Emanuel, thank you so much for accepting the invitation. So please, go ahead.
Thank you, Celso. Okay, I see that this is working. Good morning, welcome. Thank you for being here this early. Well, Celso already told you, my name is Emanuel, and it's good to be here back at this nice place. I don't really know what I'm doing here, because I should be speaking about Bose-Einstein condensates in a quantum computing school. And although we have a truly quantum platform, I don't think this is the future of quantum computers. Yes, Celso?
This school is quantum computing school, but the director asked us to give some courses about quantum technologies in general. So this is why you are here, because
okay.
sensors.
Now I know I am here. In the end, you know, we go through Bose-Einstein condensation, and this is, as I told you, a truly quantum platform, but, you know, these are very delicate systems from the experimental point of view. So they're not really scalable or useful when you want to do, you know, large scale measurements or large scale computation. But still is a quantum platform. So my agreement with you, I think, is I present you the platform. I present you what we've been doing with this. And you might think of applications. You might think of new technologies to do with this. Okay? Good. We have, I designed a roadmap of well, I had 3 classes, but I designed three lectures. So today I'm talking about basics of Bose-Einstein condensation. And I'm going really through basics because I've been asking around at my home institute, and not everyone, even PhD students, have been have seen this before. So we're doing a more basic lecture today, and I'm sorry if you have seen this, so I think it will be important for everyone else. So tomorrow we start playing with Bose-Einstein condensates, and it's a kind of overview of the field. And on Friday we dive deeper with interactions. Okay, so this is my roadmap. As I told you, I have prepared 3 self-contained lectures. I hope to get to 10:30 at the end of my lecture here. But if I don't, I don't mind, okay? Ask questions. If we don't get to the end, we get to the end tomorrow. It's fine, okay? So as Celso told you, raise your hand, we get you a microphone, and so your question is registered on YouTube. Okay, good. So, basics of Bose-Einstein condensation. If I ask around here, what is a Bose-Einstein condensate, or what is this transition to Bose-Einstein condensation? If I ask you, can anyone give me an answer? Can anyone, you know, try it? If I ask and you don't know, I'm sure you are looking for the answer in, you know, reliable sources of information, no? Like, I don't know, ChatGPT. That's what we do today, no? So this is what I did. I asked ChatGPT, to give me this answer. What's Bose-Einstein condensation? And it gave me this, this answer. It's there, it's really from it. Just the bold is mine. Okay, Bose-Einstein condensate is this state of matter made of a large fraction, a large number of particles, where all of them go to a single quantum state. Okay, usually the lowest quantum state. And they lose their individualities, so they act as a single quantum entity. So this is ChatGPT definition. I think I couldn't do better. Okay, but the computer told me more. It told me that okay, they lose the individualities, and they display quantum phenomena on a macroscopic level. Every time I think about a quantum system, I think about an atom, and this is a very small scale system. BC is a large in quantum, no, in the quantum world, a large quantum object. And I think this is what makes it very, very interesting. Okay, and then of course, it gives me also key properties of a BC. Maybe the most interesting of it is superfluidity. We come back to this at some point. And it has also given me the historical context. Next, it's from 1925. So next year, the prediction for Bose-Einstein condensation from Bose and Einstein turns 100 years old. And actually, it turns 30 years old from an experimental point of view. So it took 70 years to realize the predictions of Bose-Einstein condensation. And I think it will become clear why. Okay, good. So it's a general definition. Let's look at it in more detail. I have a problem, actually, with this definition, that it says you have a group of particles, and when I think about a group of particles, I know I have to treat them statistically. I have to do a statistical treatment of this problem. And when I think about statistics, I think about the coin tossing problem, no? Half of the times it will be in one state, half of the times it will be in the other state. And that I have many states, I just fill the many states with a fraction of my particles, a very small fraction. So it's odd that I have a very, very large number of particles going to a single state. And I think this is the beauty of what we're doing here. Bose-Einstein condensation is this, that ChatGPT told us, is this macroscopic occupation of a single level, so it's a phase transition. But it's completely driven by the statistics. It has nothing to do with interactions. It has nothing to do with external potentials. It's only due to the statistical description of my system. Okay, that's a statistical consequence. So that's what we do. So let's see how to solve this problem statistically. So we solve now the non-interacting BEC in a box. This is a very basic problem, and you see that I'm writing simple expressions. Most of you might have seen it at some point. But this, believe me, this pays off because afterwards we use the same, almost the same expression to treat the, I'm sorry, it's the interacting BEC in a trap. There is the non, okay, it's interacting BEC. No, it's the non-interacting BEC in a trap. So we trap without interactions, sorry. And then later on, we do the trapped interacting BEC, okay? So This is what I want to do today. Okay, we start with the non-interacting BC in a box, and we go to the blackboard. Okay, so I have, if my letter is like this, you in the back, you see, fine, okay. So we are treating the non-interacting BC, okay, in a box. Because when we do statistics, everything, most of what we do, it's in a box. I have n particles. And they have to spread themselves in the several states of the system. So I'll tell that the n particles spread in the states. So this n, this small n, is just the occupation of a single state. So if I sum all of the occupations of all of them, I have all the particles of my system, okay? Also, each one of these states has an energy, an individual energy. So I can also compute the total energy of my system. So it's this thing, where this is the energy of this state, okay? It's very simple. Good. I can work this out, and I use this to write the occupation numbers, okay? The individual occupation numbers of the states. So when I write this, I have so this is how we write the individual occupation numbers of the states of the system. To write this, we have to equate from this to that, we had imposed a few restrictions. One, our particles are indistinguishable. Here's an S. Okay, and two, there are no restrictions on this. Okay, I think these are the two restrictions that I had. Yes, okay. Why I'm writing this here? If I change this, if I impose restrictions on the occupation number, instead of bosons, I have fermions. For fermions, I can have only one particle per state. This you know, it's Pauli exclusion principle. So 1 or 0. Here I have no restriction, so I can add as many particles as I like. And they are indistinguishable. This is the quantum way of counting things. No, statistics is about counting things. So if they are distinguishable, I have Boltzmann statistics. That's the whole point. Okay, good. Fine. When I write this, there are new letters here. First, T, it's temperature, so regular temperature of my system. And me, that is chemical potential. So me, we define it as the chemical potential. And what's chemical potential from a thermodynamic point of view? Anyone? The chemical potential is just the energy cost to add a new particle to my system. Okay, if I want to add a particle, I have to pay this cost. So me is the total energy, dN. I think it's like this, okay. Okay? I think nothing much new here. Good. But when I write this, occupation number, and I look at it carefully, I have some, I discover some restrictions on the chemical potential. The first restriction is that it's always smaller than the energy levels. If it's larger, okay, if it's larger, this number it becomes negative because this becomes less than 1. And this is not possible because this is occupation number, this is number of particles. So me is always smaller than any energy of the system, any energy of the individual levels, okay? Good. But the lowest energy level, this applies also to the lowest energy level. So me is actually the upper bound of me is the ground state energy level. Okay, I think that's clear from this definition. Good. The other thing that it's not obvious, but we can take from here is that if temperature is very high, this becomes the Boltzmann distribution, as you expect. So the classical Boltzmann distribution. Okay. Good. So I have any particles. This is how they fit in the levels, and I'm in a box. Now I want to solve this problem from a quantum mechanical point of view. So we are solving the n-particle problem in the box. In quantum mechanics, you probably solve this in your undergraduate course. So, good. So we solve it. I write basic expressions, and I'm sure you have seen them before. But again, I use them later. So that's why I write now, okay? Good. So since they are non-interacting, I can solve for one particle, and that's the same for n particles. What's the Hamiltonian of this problem? The Hamiltonian of this problem is this. Nothing else. No? That's how we write it. You know how to solve this also, no? If I solve Schrödinger equation with this, you have plane waves. Oh? And we can write the plane waves like this. Let me get my notebook. Okay, good. And here V is the volume of the box. So V is the volume of the box. And you know that the K, you cannot have any K. K is restricted to some quantized values. K is a vector that is written like this. These are the sizes of the box. So if I multiply the 3, I have the volume. And the n's, nx, ny, and nz are integer numbers. So 1, 2, 3, 4, and so on. Okay, good. So where am I now? So I can, with this, so I have solved, and I'm sure you have solved this at some point. I can write the individual energy levels, the energy of the levels. And I write them here. And you know. And of course, if I take the absolute value of k square, it's this square plus this square plus this square, nothing else. Okay? I think I don't have to write that. This is not new for everyone. This is okay. And now we start to go to momentum space. So this is, we have written the Hamiltonian, the wave function, how k is defined, the energy. I want to count states now. So my states are dependent on k. So if I have a k space, I can write the number of states. I think I should, I write this. The number of states in a volume d3k. So I think I don't have to draw this. If I have, please tell me. But if you go to k space, no, kx, ky, kz, the states allowed for this system are points. No, you cannot be anywhere in this space. So in the end, I'm counting how many points allowed for my system I have in a volume d3k in this space. Okay, this is the calculation what to do, and this is not very difficult, but you get this thing. Okay, this is the number of states in this volume. Good, but I don't have really to be in K space. I can go to energy space because I know the relation, where is it? Here, between K and E. So knowing how many states I have in a volume d3k is the same of computing how many states I have in a shell, in the energy state, between an energy E and an energy E plus dE. Okay, that's and I can do it. It's a simple calculation, and we get an expression that is like this. I can write here. People that see it, okay. E half dE over square root of 2 pi square 8 bar cubed. Okay, good. That's where I wanted to be, because, you know, remember, this is the number of states in a shell that is dE thick, okay? So I define this quantity as the density of states. This is what I wanted to do, okay? So the density of states. Density of states. This will appear again for us soon. Okay, density of states is just M to the 3/2 E half over square root of 2 pi square over h bar cube. Okay, this is what I wanted. I keep it here. Good. Okay. As I grow energy, as I go up in energy, states are getting closer and closer to each other. Do you see this? So it's getting denser in energy, okay? The energy levels start to approach each other. Now, so I have ground state, second, third, and then they start approaching as I grow in energy, because the density is increasing. Easy to see. Good. If I have many states, this looks like a continuum of states. So I can exchange, and this is what we will do, I can exchange all these sums by integrals. Do you see? Everyone is with me on that. Okay, that's what we want. Okay. But there is a caveat on that. So this is not completely true. Because we can actually compute how this chemical potential is behaving with like temperature. So what's the cost of energy to add a particle as a function of temperature? And of course, it's always below the ground state energy. But as I lower my temperature, remember, we are looking for Bose-Einstein condensation, so we're going down in temperature. When I go down in temperature, the chemical potential approaches the energy of the ground state. But when I do that, when I approach the energy of the ground state, this thing approaches 0, this thing approaches 1, this number, the N0, explodes, it diverges. Do you see this? Okay, so I cannot really treat the ground state as I treat the other system, the other states, because the occupation number starts to diverge. It's not like I have a few particles in the states all the time. No, the ground state doesn't behave like this. So when I write this to transform it in an integral, I have to single out the ground state and sum all the other states. And these all other states, it's what's becoming an integral. Okay? So I write this explicitly now. So I write. I promise I go to the other side to help you. Okay? I write the number of atoms in my system as the number of atoms in the ground state plus this sum that is now runs over every state but the 0 of the Ni, but this is Ni is 1 over exponential of EI minus me over KBT minus 1. Okay, and now I transform this into a integral. Okay, to transform this to an integral, I write it like this. So the total number of atoms are the atoms in the ground state plus V over 2 pi cube integral of density of states dE and then this term. Okay, so instead of summing individual terms, they go closer and closer to each other, so this looks like a continuum. I substitute by a density. This is density of states. This is all what we did. Everyone is following, I hope. Okay, I see people doing like this. Okay, good. We can solve this integral, and I'll go to that side. Okay, we can solve it. I will indicate the steps I'm doing, but they are straightforward, okay? So I write beta equals 1 over kBt, but this is usual, no? I'm writing also exponential of beta mu equal z, and I'm writing beta e equal x, okay. When I do that, this, so I write this integral, I'm calling it the number of thermal atoms. So these are atoms in the ground state, these are all the other atoms. Okay, this NT, this, when I do it, this NT, it becomes V over 2 pi cube mkBt to the 3/2, and then the usual terms, and okay, and then integral of x to the half dx z minus 1 ex minus 1. Guess what? One can solve this integral. It's solvable. Okay, we write this, and this is actually a class of functions that's called Bose functions. Okay, guess why? No. So I can really write the number of thermal atoms, but before writing it, I want to tell you that this quantity, this prefactor, apart from the volume, it is so this is of course this has no units, so this has to be the inverse of a volume. So this is a distance to the cube, okay? And we define this distance as a wavelength, what we call a de Broglie thermal wavelength. It's the equivalent of the Broglie wavelength, but with the dependence on the temperature. Okay, so I am defining the Broglie thermal wavelength, which is like this: 2 pi t square, 2 pi 8 square mkBt to the half, okay? And this integral becomes then number of thermal atoms is volume over the Broglie wavelength to the cube, and these are the Bose functions. This is actually one of them, so this is the 3/2. It's a whole class of functions. I'm not where are my glasses? It's not, I'm not going into that, but there is a whole mathematical field on this. And the argument of this, I want to single this out because this is important to me, is me over KBT. Very good. This is what I wanted. Now comes the magic. It's fine. So you see, again, we have the total number of atoms, atoms in the ground state, plus atoms out of the ground state. This is the sum of all atoms in the ground state. As I lower temperature, when I lower temperature, the chemical potential goes up. But it has a limit to go up, which is the energy of the ground state. Okay? If it's the energy of the ground state, sorry, the microphone, please.
G3 half, what means?
It's the Bose function. So G
is the density of
no,
state.
I'm sorry. Too many letters. Okay. G there is density of states.
Okay.
But this G to the index here is, these are a class of functions called Bose functions.
Okay.
Okay. They come from this integral. Okay, so if I just plug in a general exponent and so on, you get the G to the 5 halves or G to the, I don't know, 7 halves and so on. Okay, it's just like this. I'm sorry. But
okay, thank you.
Thank you. Okay, so as I lower temperature, because we're trying to understand what happens at low temperature, because ChatGPT told us this is where Bose-Einstein condensation should occur. The chemical potential, so as T goes to 0, as T goes down, no, the chemical potential goes to the energy of the ground state. Okay? And for the sake of simplicity here, we can do this. This is approximately 0. Okay, it's just the ground state. We can lift this restriction. It's not a problem. I just want to add this here. So what I have here is the number of thermal atoms is G3/2 of 1. And this is a number. Okay? So the number of thermal atoms at this condition is thermal to the cube, G3/2 of 1. And this is a number that is 2, 6, 12. I write it. What is here? The thermal cube, 2. This is not 2,000, it's 2,6, okay? Why this is important? Yes, please. I think it's off.
Okay, I got it now. In this expression, n goes to 0, but t is also going to 0. Is it possible to prove that?
M goes to 0.
Yes, but t also goes to 0 in the exponential, right? In the denominator.
Yes, so you're right. So I'm looking for very low temperatures, but not really T equals 0.
Oh, okay, okay.
Okay?
So it's possible to prove that me goes to 0 faster than
Let's do
T.
differently, okay? As T goes to a finite temperature, a critical temperature that is very low. Okay, not 0.
Thank you.
It's better. Thank you. Okay, so we're lowering the temperature of the system. Good. What's the physical meaning of that? Yes,
T
Celso.
equals 0 is not possible, right?
T equals 0 is not possible thermodynamically, no? This we know. I think this we all know. But we can always take limits, no?
Yeah, sure.
Okay. Let's see, where am I? Okay. What's the point of this expression? The point of this expression is that, okay, V is the volume of the box. This is fixed. The thermal wavelength given a temperature is fixed. So this is a fixed and finite number. Meaning that the number of atoms that fit in the excited levels is limited. You cannot go above a given limit. Given a temperature, you will, add your atoms according to the statistical rules, and they don't fit anymore in the excited levels. Where do they go? To the ground state. Everyone is getting this? Okay, so Bose-Einstein condensation is like feeling. It's like filling the elevator of the hotel. It doesn't fit more than 8 persons. So it doesn't fit. You don't get in. You go to the other one. So it's not possible to get any more in the excited states. And what's the cost of adding another particle to the system, to the ground state? So if I want to start adding particles, they go to the states, they go to the states, they go to the states. Every state has a very minimal occupation. This is statistical. At some point, they don't fit anymore, they have to go to the ground. And then every single next particle is going to the ground state. So what I start to have a macroscopic occupation of the ground state. This is Bose-Einstein condensation. I don't need interactions. I don't need an external field. I just need, literally, I just need to know how to count particles. Okay, good. But there is more on that. How do I define the critical temperature where this starts to happen? How do I define it? I want to come back to that expression. So, the total number of atoms is atoms in the ground state plus everything else, okay? If I'm above critical temperature, if I'm whatever it is, my temperature of the system, this number is very low. As in any statistical system, each state gets a very low number of particles, okay? So this is very low, and the individual occupation numbers is very low. So if I'm above the critical temperature, essentially the total number of atoms is thermal atoms, because this number is very low. Do you get it? Okay, good. So I will equate this total number of atoms to this. Because when this happens, this is, if I get the condition where this happens, I'm getting the lowest temperature before Bose-Einstein condensation. If I go in a temperature below that, then this number is larger, and this equality is not valid anymore. Okay, that's my point. So I'm writing N equal N thermal and this is when T equals Tc, critical temperature for Bose-Einstein condensation. Okay, I can do it, and when I do it, let's see, I get this. So N over V times the Broglie thermal wavelength to the cube is 2.612. This is density. So density, remember, this is number of particles per volume. But what's this? This is, I'll be informal here. This is the volume of the particle, because this is the Broglie wavelength that is associated to the particle to the cube. So in a sense, this is this quantity is number of particles per volume of a single particle, per the Broglie wavelength to the cube. Okay, or how many particles fit in the size of a particle, and the size of a particle now is the extent of the wave function that defines it. When I get it on the order of 1, so when two particles that have, this has the Broglie wavelength, this has the Broglie wavelength, when they start overlapping, I get Bose-Einstein condensation. Do you see this? Do you see this? Okay, good. So I can, with this, I can just, so you know that temperature is inside here, so I can invert this expression and get critical temperature, and this is written like this. Critical temperature is written like this. 2 pi h bar square mkb. When you don't understand your own letter, it's hard. Density over 2,612 to 2/3. Okay, this is critical temperature. To fulfill this condition, all the atoms are essentially in the thermal states, or the occupation number of this is negligible. Okay? We can sketch those. I think I could do it. We can sketch N0 and N thermal as a function of T, or let's say me, because as T goes down, me goes up, but it reaches a limit which is E0, no? This is, N thermal does like this, and it saturates. So it doesn't fit anymore. N0, this is N thermal. N0 goes like this. This is N0. If you are more visual, this is Bose-Einstein condensation. No, atoms don't fit anymore in the excited state. Good. I was saying we're physicists. I don't know if everyone is a physicist, but we are scientists in general, so we like to plug numbers and look what are orders of magnitude of this. This is what people did a long time ago. And people plugged in numbers for liquid helium. because liquid helium at some point in the 30s and 40s was behaving in a very strange way. It was becoming a superfluid and so on. And if you plug numbers for liquid helium, density, mass, and that's it, you know what you get for critical temperature? Critical temperature for liquid helium is around 2 Kelvin. This is liquid helium. What's around 2 Kelvin for liquid helium? It's 2.17, where liquid helium becomes a superfluid. So at some point, people realized that Bose-Einstein condensate was not a mathematical thing, had something to do with this quantum phenomena that we started to see in the lab. But as usual, liquids are very, very complicated. It's not clear that everything is really applicable. When we do it for a gas, because we were solving a problem of a gas, in a box, and you plug in mass like hydrogen, densities that are achievable in a gas, you get temperatures on the order of micro to nanokelvin. And that's the reason why it took so long to reach Bose-Einstein condensation in gases. How do you cool a system, a gas, to such low temperature, keeping it as a gas? Because if I ask you, let's cool a gas, let's make it colder and colder, it becomes a liquid, and it becomes a solid. So at some point you have to figure out how to cool this down a lot and avoid it becoming a liquid. So that's why it took so long. Okay, let's go back to the slides a bit. So let's summarize what we did so far. So this is a purely statistical phase transition. I think you are convinced that it's the macroscopic operation of the ground state. We have this condition to define the critical temperature, but I like also because it really shows that matter waves are overlapping. Individual matter waves are overlapping. And of course, we got critical temperature. And everything we did, I think it can be summarized in this cartoon that is very old, so I think you might have seen it before. But when we have high temperature, where is my laser point? Where is my pointer? Here. When I have high temperature, my gas, the atoms in my gas, they work just like billiard balls. This is a first-year problem in the physics undergraduate course. Now we treat billiard balls in a box. Then at low temperature, the de Broglie wavelength starts to show up. So you see, it goes with T to minus half. It's here somewhere. Yes, it's here. So as I lower temperature, the Broglie wavelength, the thermal de Broglie wavelength goes up. At some critical temperature, these starts to overlap. So I have more than one particle, it's here, more than one particle per volume occupied by a single particle. So in the end, if I could reach zero temperature, I cannot, but if I could reach zero temperature, I have what we call a giant matter wave. This is Bose-Einstein condensation. Good? Fine. Okay, we summarize our first part. I have a second part. It became clear that to really do it in a gas, we had to trap them. We had to create boxes. Restrict the atoms in a volume and treat this problem to understand what's happening in a trap. So this is what we do now. So we treat the non-interacting BC, in a trap, and this has been solved. No, sorry. What changes? I told you who solved this before. What changes, actually? The Hamiltonian. No? We solved this problem here. It's only changing the Hamiltonian. I'm adding an external field, whatever it is. I don't care about the nature of this now. That is restricting the volume occupied by the atoms. Of course, the wave functions change. We don't have any more plane waves, but we have the solution of this problem. You probably have solved the harmonic oscillator or the, I don't know what, the finite box. No? That's what we do. And the energy levels, they change also from this to the energy spectrum of the trap. Of course, depends on the trap. And the density of states change from this to something that looks like this. In the end, what the trap is doing is restricting the energy volume available for the particles. But when we do it, everything else is almost the same. So all these calculations that I did here, the steps are the same. Of course, depending on the specifics of your trap, you get difficult calculations, or you get a difficult integral to be, solved. But that's it. So all the steps we did are the same. And this problem has been solved by Professor Banhato, which is a professor at the Institute of Physics in São Carlos, in 1987, not 1987. I was alive, Celso also, but I don't know if any of you. And he solved this for a generic power law trap. So this is a very, very beautiful paper that one can really get it and equate it from the beginning to the end. And this is a power law trap. So if you substitute these numbers, E1, E2, E3, P, L, Q, A, B, C by the proper numbers, you get harmonic trap, 1D, 2D, 3D, you get the box, you get a linear trap, you get whatever you like. So you get possible traps. At that point, this is a historical note, at that point they were interested in linear traps, because linear traps were real to trap charged particles. So it turned out this is not possible, but they did, and they solved. And you know what? We got this condition for the box. No? I think I convinced you that we got this condition for the box. You know what this condition becomes when you get a trap? It becomes this. You know what's changing? Instead of the product of the density per the cubic, the cube power, the third power of the de Broglie wavelength being this number, it's the peak density. So at the bottom, if I have a trap, I have the bottom of the trap. This is the place where the density is higher. This is easy to understand. The density of this, the density at this point times the power cube of the Broglie wavelength is still 2.612. So if I reach this condition at the center of the trap, I get Bose-Einstein condensation. What's the critical temperature? They are more complicated. But still, one can really work this out in a few hours of solving equations, solving integrals. Okay? And this is the beauty of this problem. I still get Bose-Einstein condensation. I still get the same, essentially the same condition to understand the overlapping matter waves when I have a trap restricting the volume available to my atoms. Up to this point, are we fine? Okay, good. Okay, at this point, there was a large effort to not only trap those atoms, experimental effort, but also cool them down. Because at this point in the 80s, we had lasers. So we start to understand that lasers were the way to cool atoms down to very, very, very low temperatures. Okay, so Bose-Einstein condensation is a possibility. But it soon became clear that interactions are both unavoidable in our system and the solution to cooling. So I cannot really cool a gas down. Give me a minute and I open for you. I cannot really cool a gas down without interactions. And actually, I cannot, it's not 100% true, but I cannot switch off interactions. So I have to treat the problem of the quantum the gas in a box or in a trap with interactions. Okay, that's the third part of our conversation here, please.
I don't know if there is any special reason for this, but this expression that Beniato found is above.
This.
Yeah, the generic power law is like a known result that is used in mathematics, because if you see, if you don't think about the coefficients, you may see that is similar to a LP norm, right?
Okay.
So this is what's called like a weighted anisotropic LP norm. So basically, in the sense of mathematics, is like you have like a Soloviev space, and there are different contributions in different axes. Do you think that in the physical sense, what this means in the relation with the mathematics of it?
I may have said this wrong. So he didn't found this.
Okay.
He was, okay, let's suppose we have a generic trap. So this is a generic way to write an external potential that traps the atom.
Okay.
Okay. So maybe the reason why he wrote this is the same reason you have.
It makes sense, because like if you think mathematically, it was like the different contributions in the different directions. So it's a cool way to generalize this. Very interesting.
Good.
Thank you.
Thank you. Okay, we move on. We move to treat the problem with interactions. So interacting BC in a trap. I think now I come back to the blackboard. Yes. Just give me a minute to clean up here. So for treating this problem, I do it in a more straightforward way. To treat the problem upside down. What we did right now, also on these calculations, was to write the full system, number of atoms, and how many are in the ground state, how many are in the excited state. So I'm treating it upside down, which means I'm writing my quantum field, if you like, already with the imposing that most of my atoms are in the ground state. Because I think you are convinced that atoms go to the ground state. So I'm just treating the system in a quantum way. Okay, so let's do it. So I can write my boson field. So I'm treating the interacting BC in a trap. So I'm writing a boson field that is the field for the ground state and the usual, this is the usual notation of creation and annihilation operators. If you're not used to it, don't worry. We're just writing, but we don't do much with it. Plus the sum over all other states. So, like this. So this, and I'm starting already thinking that most of my particles are in the ground state. So this is ground state, and these are what we call, in this context, thermal fluctuations. Actually, not thermal like this. I prefer, because I use this afterwards, quantum fluctuations. Okay, so this is how we write it. If most of my atoms are here, I can exchange the creation and annihilation operators by the number of particles in that state. Okay, that's an approximation. So I can write these guys actually like this: square root of the number of atoms in the ground state, which means this. So the expectation value is just the number of atoms in the ground state, okay? There is nothing much strange here, and we are on this saying that this is much larger than 1, so this is very large. This is comparable to the total number of atoms. Of course, if I'm telling that all of my atoms are in the ground state, this means I'm neglecting quantum fluctuations. So I'm saying, okay, this doesn't matter. This matters, and we come back to this on our third lecture. So be here by Friday. But for now, we are throwing this away and staying only with that. This is not really, this might sound strange, but it's really not strange. This is what we do when we change our view of photons, which are particles in one mode of the electromagnetic field, to electric and magnetic fields. You say you have a lot of photons in the same mode, so I'm changing a quantum field by a classical field. This is what I'm going to do. I'm changing this from quantum to a classical field. So this is what we do when we change from photons to electrics and magnetic fields, okay? Or an electromagnetic field. Good. Okay. How can I define the evolution of a field? Heisenberg equation. Is that strange for anyone? Heisenberg equation, okay? So we write like this. I h bar d psi dt equals, it's the commutator of this with the Hamiltonian of my system, okay? In a quantum mechanics course, you get that. So if I write this, I just need to know what's the Hamiltonian of my system I just need to know the Hamiltonian of my system. I know that the evolution of my field. Okay, that's it. What's the Hamiltonian of the system? I want to be short here, but I have kinetic energy. You know how to write kinetic energy. You have external fields that I'm writing external because you don't really need to have a trap. So this is our trap, but can be other fields also. And you have interactions. How do I treat interactions like this? How do I treat the interaction of the atoms with all the other atoms in my system? To treat this, well, treating this is a very difficult problem. So to treat this, we change interactions to a two-body interaction. So in other words, I'm treating not any gas, and I'm writing this here, but I'm treating a dilute gas. So the mean distance between the particles is very large. So when they meet each other, it's a two particles encounter. They don't meet in 3, or they don't meet in 4. It's not likely. So I'm writing the interaction term in a dilute gas. So density is low. Okay. Actually, this is why we can cool it down and not becoming a liquid. Because becoming a liquid, it's really 3 particles together, and then you have a droplet. Okay. So when I write this, I have a term that is like this. There's more to this integral, and this U is the interaction potential between 2 particles. D3R prime. I think is this. Yes. This is the interaction term. Problem is, what is this? What is the interaction potential? I have 2 questions, so I get this, excuse me. Where? Here. Yes. Please.
First, when you wrote the bosonic field in this term, are you considering that there is a conjugate part associated? It's just that.
No, there is the conjugate. There is the conjugate
okay.
part of it.
Because just thinking about like.
Yeah, this is something that I should have said before. I'm experimentalist, so some of the the calculations are overlooked. Okay. Yes.
Sorry. When somebody study superconducting with London theory,
okay.
One find an order parameter. I would like to ask how different is this C function in which you are writing with?
We call it an order parameter.
Yeah. It's the order parameter.
It's the order parameter. I'm not getting to the end, but for all practical purpose, you can look at this as Schrödinger's wave function, but it's really an order parameter. It's not, for mathematical reasons, it's not a wave function. No, so it's not
Yes.
But for your mental model of this, you can think of this as a wave function.
And the other one is, can I treat the interaction in this case like a mean field?
We will get to that.
Okay.
Okay, we'll
Okay,
get to
okay,
that. Exactly this. So
Thanks.
we get to that. Okay, so I'm treating this as interactions in pairs, but I still have a problem here. I still have a potential that I don't know how to treat. And then how do I treat the interaction between two atoms in a quantum way? Anyone? You have to do scattering, no? Wave scattering. Let me ask, did anyone did wave scattering here at your home institute? Okay, I have to. I went to my calculations to see, okay, how much I can add this in this class. And then you start here, you go to the end, and there are like 20, 25 pages of calculations of phase shifts and so on. So I decided not to do it. I do what I call a crash course on interactions, okay, on wave scattering. Let me do it quickly, and I promise I end in time. So it's really a crash course on quantum scattering. I have an incoming wave. This is a particle, you know, it's moving. And if there is nothing in the middle, it will just go on move. No, this is a plane wave. It's nothing else. If I add here a scattering potential, another particle that is, we think of it as this is moving, this is steady here, which means we are really treating this problem in the center of mass. No. The wave that goes out is not anymore this. The wave that goes out is shifted compared to this. Do you see this? It's changed because I had something that happened in the middle. Okay? So if I look very far away, I have a wave that is shifted, and this is a phase shift. Okay? Okay, fine. We can compute those phase shifts if this potential here, if this scattering potential is bounded, is finite for large distances, for large r, and I think there is another condition. Yes, no, I think it's like this. So that's usually true. That's usually true because the usual potentials of interaction are like van der Waals interactions. So 1 over R6, 1 over R12. So this has a finite range. Okay. Also, I can compute those phase shifts, but I have a limit if I'm doing a low energy collision. Well, that's also true because we are in a low energy condition. This phase shift is a sum, but in low energies I keep only the lowest, the first term of the sum, which is called the S wave scattering. Okay? So I keep only as energy is low, I keep only the only one that survives is the S wave scattering. And this has a very convenient way to write it, because it carries a delta function on it. So I get rid of the integrals. Okay? So a potential that is like this in the low energy limit can be substituted by a potential that is exactly like the billiard ball potential, a hard sphere potential. It's the same. Okay? So I can exchange U by an effective potential, that is written like this. 4 pi h bar square A over M delta R minus R prime. 4 pi h bar square M, you know everything. A is what we call S wave scattering length. Is a parameter that depends on the specifics of the potential. So if I have 2 hydrogen atoms, or 2 sodium atoms, or 2 whatever atoms, this A is different. But it carries this Dirac delta inside it. So I get rid of this integral here. In between this and this, there are really 25 pages of calculations. It's the hell. I know that Celso teach this at UFSCar, and I know that he knows this. Okay, good. If I plug in everything, I get my equation that defines interacting BCs in a trap. So I'm writing this here. I get I8 bar d dt, and now I'm substituting C, which is the full field, by C0, that is the classical field that represents all particles in the ground state. So in a sense, when I write this here, this is not an operator anymore, but this is a field it's like a single body wave function, but it's representing n particles in the same quantum wave function, okay? So this is what we call a many-body wave function. Where am I? Here. Minus A2, so kinetic energy. When I do that, plus external. I'm not writing trapping anymore. This is on purpose. So this depends on position and time. And the interaction that is now treated like this. Oops, this squared, psi squared. I'm getting to the end, okay? So as you see, I have time dependence of my many-body wave function, kinetic energy, external potential, interaction. What I like most of this is this looks like Schrödinger equation. So if you are in an undergraduate course, you know the meaning of this. It's not 100% true because, again, this is not really a wave function. This is the order parameter of the system. And this is representing n times the wave function, the real wave function of a single body, okay? But you can look at this equation and see that this is the time evolution of this object in an external potential subjected to another potential that we call a mean field potential that is created by the interactions of all other particles. Do you get it? This has been derived independently by Gross and Pitaevsky. That's why it's called the Gross-Pitaevsky equation. Gross-Pitaevsky equation. And this is the term is not correct, but this is the master equation, not by master, no. This is the main equation to treat Bose-Einstein condensates. Actually, every single experiment is exactly modeled by this, but 1%. What is this 1%? Here. It's powerful. Just to get to a point where we can stop, because I'm in my time, we can do the usual time-dependent solution. No, which means we can write it like this. I mu t over 8 bar. Is this? Is like this? I think I miss. No, it's right. No, this is the usual solution for the time-dependent Schrödinger equation. No, the time-independent times this. And look, usually we write the energy of the state. Here is the chemical potential. Okay, that's what we did there in the back. The chemical potential is the energy of the ground state. When we write this, we get the time-independent Gross-Pitaevsky equation, and this is where I will stop. So psi 0 equals minus h bar square over 2m. Now this psi 0 is independent of the time, so maybe I write here that this is time dependent. Plus external psi 0 plus I will exchange this by an effective, so a coupling constant. Is it too low here, or is it fine? Okay, good. So again, and to finish this, what I like this is if I exclude this term, this is Schrödinger's equation. You know how to solve it. You know how to interpret it. The devil lives in the details. This is the dominant term, and it's nonlinear. But still, you understand the meaning, okay? So I had a few more for this class, but I keep it to tomorrow. So tomorrow we start, from tomorrow we start from this point, okay? I'll be here for the whole day if you like to talk, and I thank you for your attention.
Further questions?
There is any soliton solutions to
There
this?
is. We come to this.
Okay.
Any other?
You have to turn on.
I'm sorry if I missed this part, but when you write psi 0, you're writing order equation only from the ground state. So
Yes.
it's the number, your mean order would be the number of particles on the ground state. So.
Yes. So this equation is not valid for a few particles, let's say. I have to have many particles, all of them in the ground state. Everything that we do in the middle that I didn't do here, it's only valid if I have many particles in the ground state.
All right.
Okay, there is a question over there. I go. Yes.
I have one question. It's about when you present the solution of, how to say it, of Bagnoto, right? That is for a specific power law kind of trap, right?
Yes.
So it is possible to generate a, how can I say this? Like a general trap function with a linear combination of these power laws B trap, like B total equals B1 trap plus B2.
I
and
think
so
so.
on.
I think so. For practical purpose, with that expression, one can generate box, one can generate harmonic oscillator in 1, 2, 3 dimensions. One can generate linear potentials, quartic potentials, and so on. So I suppose if I have linear combinations, you will get other kinds of traps of this kind of potential. Okay.
Perfect. Thanks.
Further questions? No. Okay. If you are too shy to ask here, I'll be around. Just come by. Okay. So see you tomorrow.